Be sure for the second speaker, you have the slide from the website, right? I don't have to do anything. Yeah, right? Yeah. The slides are already there. Yeah. Okay. Yeah? Yes. Yeah. Okay. Thank you. Yeah. All the slides are right. Yeah. Oh, thank you. Okay. 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 Okay.
Okay, welcome everyone for the second session on Symmetric-Key Cryptanalysis. There will be 3 talks in these sessions. The first talk will be algebraic attacks on round-reduced terrain and full M3. This is a paper by Kei Zhang, Qingju Wang, Yu Yu, Shen Guo, and Honghui Yu. And the talk will be given by Penny.
Thanks for your introduction. Good afternoon, everyone. I'm Kai Zhang. Today I'm going to talk about our work, algebraic attacks on round-reduced ring and all AI answer. This is John with Qingyu Wang, Yu Yu, Chen Guo, and Honghui. So let's start from empty in the head project. Empty in the head is a family of zero-knowledge proofs based on MDC. It is used in a lot of post-quantum signature schemes. So roughly speaking, if I have a zero-knowledge proof and a one function, we can combine them together into a signature scheme. Let H be a one function, we sample a random input X and compute the output Y. So the secret key of the signature scheme is X, and the public key of the signature is Y. And the signature is roughly the Symmetric proof. The signer proves it knows a secret X such that H of X is Y by Symmetric proof. Here are some post-quantum signature schemes based on MPC in the head. For example, picnic, fish, winner, hammer, and more. So usually linear functions are friendly to zero-knowledge proof. For example, XOR, constant binary matrix multiplication. And nonlinear functions are usually not friendly to zero-knowledge. For example, AND gate, inverse function over finite field. So if we want to improve those signatures based on MPC head, first we can use better zero-knowledge proof. And or we can design some one functions with low non-linearity, which means we reduce the number of nonlinear functions as small as possible. And ring and AM are those one functions designed for signatures based on MPC head. So our result is that we found some non-trivial key recovery attacks on boundary reduced ring and AM3, which is the 192-bit version of AM. In our attack, we exploit the algebra structure of the power function as to the power of D. So let's introduce ring. First, we have a pair of known plain text and ciphertext. And we have some randomly selected invertible matrix. And the key refers to the secret key. The nonlinear function of ring is the inverse function over finite field with characteristic 2. So this is a typical SP network. So we first add round key X box multiplied by nonlinear multiplied by invertible matrix add round key X box matrix multiplication and round key X box, and finally the Gauss. When we use the so-called block cipher as one function, we sample a secret key to encrypt a public known plaintext to obtain the ciphertext. If the block cipher resists known plaintext attack, then it means we cannot recover the secret key from plaintext ciphertext pair. Then it implies the one-wayness of the given of the one function. So we encounter some difficulty at first. First, we have only one known plaintext and ciphertext pair. The signing process for the MPC head paradigm does not output the new pairs. It is just a zero-knowledge proof. Zero-knowledge proof ideally does not leak any information about the secret. So statistical attacks are not directly applicable, including differential attacks. So it seems that we can only perform algebraic attacks if we could attack. And the second is the S box is very large, and the linear layer unstructured. It's just a random invertible matrix. So it seems that we have no other choice. We have to analyze the algebraic structure of the S box, which is an inverse function over finite variable with characteristic 2. So this is the same type of the S box of the AS, and we know the inverse of X is equal to X to the 254 over finite field 2 to the 8 with mapping 0 to 0. And here is the most important observation. We discovered that X to the 254 equals to X to the 17 to the 14 multiplied by X to the 60. So why is this formula special? First, x to the power of 2 is linear over finite field recurrent to 2. Let L of x be the square function. Then L of Lx plus y equals to x squared plus y squared. There are two x, y, they eliminate each other. So L of x plus y equals to L of x plus L of y. So it is linear. And in fact, there exists a binary matrix such as x to the power of 2 equals to the matrix multiplication. And secondly, the multiplicative group of a finite field is adic. It means x to the 17 is a subgroup because 17 is a divisor of 255. So it means x to the 17 takes only 15 possible choices. Let's combine those two facts together. First, as to the 16 is linear, it means there exists a matrix. Secondly, the x to the 17 has only a limited number of possible choices, denoted by A. We can have x maps to S254, which is the nonlinear function of AS can be expressed as one of 15 linear mapping. In other words, the nonlinear function of AS is equivalent to the following pseudocode. The function S selects linear mapping according to the value of x to the 17. And then it multiplies the selected matrix by the input as the output. And based on the fact we didn't find any new attacks better than the scenario of that analysis on AS. However, Ring also uses a similar type of nonlinear function, which is the inverse function over finite field recurrent. So the analysis is similar. We want to find some proper parameter DST such that the inverse function over this finite field, which is S to the S minus 2, to the S to the D to the S multiplied by X to the 2 to the T, where D is the divisor of F minus 1. Luckily, we found that for even this is possible. F minus 2, which is 2 to the N minus 2, and can be written as 2 to the N minus 1 and minus 1 again. Then we apply the difference of 2 squared. We can have the following formula. So we can find proper DST. So S to the D have only 2 to the half of N minus 1 possible choice. So we can apply one rendering. So the cryptanalysis is similar. S to D has limited possible choice, and S to the D is linear. So we can enumerate all the value of S to the D. This linearizes the nonlinear function. Finally, we can solve the linear equations about the secret key. So the complexity is 2 to the half of in terms of the number of encryption, and assume the Gaussian elimination and encryption are both equal. Let's move to two-round theory. So first, linearize two aspects at the same time takes 2 to the half of N times 2 to the half of N, which is 2 to N. This is not better than brute force. So we have to come up some new ideas. We observe that for some power function, we can have some linear or quadratic constraints. For example, if we get x to the 5, which has limited number of possible choice, and suppose x to 5 is 1, then x to the 15 equals to x to the 5 to the 3 multiplied by x. Remember that x to 5 is 1. So we can have x to the 16 minus x is 0. And x to the 16 is linear, so we have some linear constraints about x. Secondly, x to the 5 can be expressed as x to the 4 multiplied by x. And x to the 4 is also linear, so we can some quadratic constraints. And so we come up with a new framework set, such that for proper parameter d, we get the value of x to d. So we can have some linear and quadratic constraints. Finally, we solve those constraints. So how to solve quadratic equations? So in general, this problem is not complete, but if we have a large number of linearly independent equations, then this equation can be solved in polynomial time. So this method is called linearization method, and for each quadratic term, so we introduce a new variable, and we replace those quadratic terms with the new variable y. Finally, we solve the linear equations of y. Okay, so we can solve two round mean. For the 128 version, we first get the value of s to the 257. We can experiment result shows that we can obtain a lot of linear equations. So we can express the secret key as some free variables. Finally, we can obtain some quadratic equation at the second expose. The input of the nonlinear function can be expressed as a linear combination of k, and the output of the nonlinear function can also be expressed as a linear combination of k. So and we know for inverse function, the input multiplied by the output is 1. So we can have a lot of quadratic equations. And finally, we solve the equations of the free variables. The complexity will be 2 to the 120. Finally, we move to AM. AM is another line function. The x is a secret input and y is output. There is no, this is not like a block type. We have only just private input and public output like y function. And the nonlinear power function is, and the power of the nonlinear power function is a Masonic prime. And the linear, and here is the linear measure. So there is a flaw in the design of AM. The inputs of all the nonlinear layers are identical. So it is possible to linearize all the nonlinear layer, all the first nonlinear layer. So we do not found proper parameter for AM1 and AM3, which is but for AM3. But for AM3, which is 192 bit version, we found proper parameter. We can get the value of s to the 45 and linearize the two expos at the first layer. We can have a lot of linear equations, can express security and free variables. We can also have a lot of quadratic equation. Finally, we can solve it. The result is 2 to the 118. Our suggestion is to add some object before the first year. And recently, the authors of AM adopt our strategy. They propose AM2, which is a fixed version. Okay, that's all. Thank you.
There any question?
One question. I just have one question. Sorry, something I didn't understand in your talk. Why you could not find parameters for AM1 and AM5, but could you give more detail? Why it only works in AM3?
It depends on the on the parameter. But the number of D must be a divisor of f minus 1, and the factorization of 2 to the n minus 1 is special. So sometimes we can find a proper divisor for green, but we cannot find proper divisor for data. But for 192, this is not a power. This is not exactly a power of 2. It has some factor like 3, so we can factor. 45 is 45 is 9, is 3 plus 3 plus 5, which is special.
Thank you. Okay. So no more question. Let's thank the speaker. Right, so the second talk of this session will be on photon speedup for multidimensional zero correlation linear distributions. This is a paper by Akinori Osoyamada.
Thank you for introduction. I'm Akinori Osoyamada, and this is a paper about how to achieve quantum speedup for multidimensional and multidimensional zero correlation linear distributions. And first of all, I'd like to explain some backgrounds from classical cryptanalysis. And I'd like to review one-dimensional linear distribution. So suppose P is a permutation which is random for some block size K. And let alpha and beta be some n-bit strips. I mean, these are some input and output linear masks. Then the linear correlation is defined by this equation. If P is random, then the absolute value of the correlation is very small. This means that if the absolute value of the correlation for some block cipher EK is very large, then the cipher can be distinguished by checking whether the proportion of x satisfying the linear equation is likely to be much larger or smaller than 1 over p. And the data and the time complexity of this distinguisher is about the inverse square of the correlation. And the idea of this one-dimensional linear distinguisher extends to multi-dimensional linear distinguisher like this. So here, let weight be some vector space which consists of many input and output linear map, alpha and beta. And suppose we have a basis alpha 1 and beta 1 and alpha 2 and beta 2 and so on. And now define a function ring of x in this way. I mean, the first bit of ring of x is the linear approximation by alpha 1 and beta 1. And the second bit of ring of x is the approximation by alpha 2 and beta 2 and so on. This function is called the multidimensional linear approximation of P. And then define some probabilistic distribution or probability function like this. P of D is the probability that the function takes the value of D when we choose x uniformly at random. And this distribution becomes very close to the uniform distribution if P is random permutation. And here there is an important fact. The fact is that if we take the sum of the squared correlations, then the value is equal to the value or capacity of distribution, this distribution. And here I don't have enough time to explain about details of capacity, but the important thing is that the capacity is strongly related to the chi-square test statistic. And so, if the sum of the squared correlation is large for some block cipher EK, then we can distinguish the block cipher by computing chi-square test statistic. Because if this value is large, then the test statistic for block cipher EK will be large. On the other hand, for random permutation P, the capacity will be very small, and so the chi-square test statistic also be very small. And so in this way, we can distinguish the block cipher EK. And the complexity of this distinguisher is something like this. The square root of the power d over capacity. And next, I'd like to explain about zero correlation linear distinguisher. So in the previous slide, I assumed that the square correlation is very large. But here, I'd like to assume that the correlation is exactly equal to 0 for some block cipher EK, and all input and output linear mass alpha and beta in the vector space V. Okay. Then the corresponding capacity will be exactly equal to 0 for real block cipher EK. On the other hand, for random permutation P, the corresponding capacity will be very small, but still non-zero with high probability. And so, again, we can distinguish the cipher EK from random by computing some pseudo-disk statistic. And the complexity is something like this. And so this is the general idea of zero correlation linear distinction. But actually, for some special cases, we can decrease the complexity further by using some interesting link to integral distinguisher. And so actually there is an interesting link between multidimensional zero correlation linear and integral distinguishers. So again, suppose that V is the vector space of input and output linear masks. And we say that input output masks are linearly independent if V is decomposed as the product like this. Here V1 is the set for input mask alpha, and V2 is the set of output linear mask beta. And multidimensional zero correlation linear distinguishers with linearly independent masks are equivalent to integral distinguishers based on balanced functions. This is a well-known fact. And here the important thing is that the equivalence holds only for integral distinguishers based on balanced functions, not zero-sum functions. I mean, so there are two types of integral distinguishers, those based on balanced functions and those based on zero-sum functions. And this equivalence holds only for balanced functions. And by using this equivalence, the complexity for multidimensional zero correlation linear distinguisher drops to this complexity. And this complexity is better than the linear complexity I explained in the previous slide. And next, I'd like to explain about the background of quantum cryptanalysis and the motivation of our research. So first, I'd like to explain attack models. In the classical setting, we use the theorem that we have an adversary with classical computer, and there is an encryption or decryption oracle. And in our paper, we assume that there is an adversary with quantum computer. And we also assume that the oracle is also quantum. I mean, the adversary can make quantum superposition queries to the oracle, and the ciphers result in quantum superposition. And next, I'd like to explain about Simon's quantum algorithm. So now, suppose we have a function f and a secret value f, and this property is satisfied. I mean, for all x, f of x plus s is equal to f of x. That is, f is a periodic function, and s is the period of f. And given the quantum oracle of f, find the secret period s. In the classical setting, it requires exponential time to solve this problem. But in the quantum setting, time shows that this problem can be solved in polynomial time. And very roughly speaking, Simon algorithm works like this. Simon algorithm does subroutine, which I would like to call Simon subroutine multiple times. And the subroutine looks like this. So it first prepares some zero state and performs some quantum operations like this. And finally, the subroutine measures the first register and discard the second register. And Simon's algorithm runs this subroutine multiple times to get multiple alpha. And then the algorithm does some linear algebra. And next, I'd like to explain about quantum amplitude amplification technique. So suppose now we have some access to Boolean function f and some unitary operator u. And let p be the probability that we get x satisfying this when we measure some quantum state like this. And we assume that this probability is very small. And what we would like to do is to amplify this probability. I mean, our goal is to build a unitary that outputs X satisfying this with high probability. Okay? And QA, quantum amplitude amplification, indeed that achieves this goal by making p to the power minus 1 over 2, which is to U as user and Boolean function F. And next, I'd like to explain about Kaplan methods quantum distinguisher. So actually, there already exists a quantum speed up for one-dimensional linear distinguisher by Kaplan method. And their technique is something like this. So firstly, they define Boolean function F in this way. Then, very roughly speaking, classical linear distinguisher is equivalent to approximately counting X, satisfying this equation. Then Kaplan et al. Applied the quantum counting algorithm to this Boolean function. Very roughly speaking, quantum counting algorithm provides a quadratic quantum speedup for counting X, satisfying the equation for some Boolean function. So in this way, Kaplan et al. Achieved a quadratic speedup for one-dimensional linear distinguisher. So there already exists a quantum speedup for one-dimensional case. And now finally, I can explain the motivation of our research. So we want the quantum speedup for multi-dimensional linear distinguishers, because if a high-dimensional approximation is available, then it makes sense to utilize it. And the best practical linear distinguishers are often multi-dimensional. And we also want a quantum speedup for multi-dimensional zero correlation and integral distinguishers. I mean, if we can find some quantum technique for multi-dimensional linear distinguishers, then it may be able to be used also for zero correlation or integral distinguishers. But here, there is an issue. The issue is that it seems hard to extend Kaplan et al. Technique to multi-dimensional cases. I mean, there already exists one-dimensional quantum distinguisher by Kaplan et al. So it would be very natural to try to extend this distinguisher, this technique, to multi-dimensional case. But the problem is that it is hard to extend their technique to multi-dimensional case, because the core of their technique is to count some set or some Boolean function X. And multi-dimensional linear distinguishers are essentially the chi-square test. And it is very unclear whether there exists such a Boolean function corresponding to such statistic test. And so there is an issue, and we need a new quantum technique. And so next, I'd like to explain about our new quantum technique, about how to extract linear correlation into quantum amplitude. So to achieve some quantum speedup for multi-dimensional linear distinguisher, we focus on Fourier transforms, because both of linear correlation and quantum computation have some strong relationship with Fourier transform. And there are two important facts. The first fact is linear correlation is proportional to the Fourier transform of a function derived from P. And the second factor is that the source of some exponential quantum speedup by Simon's algorithm and Schwarz algorithm and materialized algorithms are based on quantum Fourier transform. And so, after seeing these facts, we try to find some new quantum technique to directly connect linear correlation and quantum computation via Fourier transform. And after some investigations, we found that we can indeed observe such strong relationship between linear correlation and quantum computation directly via Fourier transform when we slightly modify Simon's subroutine. So recall that Simon's subroutine looks like this. So we perform some quantum operation and measure the first register and discard the second register. But here, I'd like to modify the subroutine like this. I mean, I do not discard the second register, but perform some additional operation here. Then, after some computation, we can confirm that the quantum state after the operations seems like this. I mean, the linear correlation of F appears in the quantum amplitude. And the important thing is that this property holds not only for periodic function F, but also for all arbitrary functions. And so, in this way, by slightly modifying Simon's subroutine, we can indeed observe the strong relationship between quantum computation and linear correlation. And we achieved some quantum speedup for multi-dimensional linear distinguisher by using this property. And I'd like to call this algorithm CEA, or correlation extraction algorithm, because it extracts correlations in quantum amplitudes. And next, I'd like to explain how to use the CEA and quantum amplitude amplification to speed up various distributions. So now, again, suppose that we have some vector space V of input and output linear mass for some multi-dimensional linear approximation. And assume that the capacity of some block cipher is very large. Then define a Boolean function like this. Then the probability that we obtain alpha and beta satisfying this equation when we measure the quantum state produced by CEA is equal to the capacity over 2 to the power n. So this probability is very small, but here I would like to amplify this probability by using quantum amplitude amplification. And if QAA is applied on CEA and this Boolean function with this many iteration, then alpha and beta satisfying the equation is obtained with high probability if the orable is real cipher, but with low probability if the orable is random. And so in this way, we can perform some quantum multi-dimensional linear distributions. And the complexity for general case is something like this. But actually, for some special cases, we can further decrease the complexity. I mean, if the input-output mass are linearly independent or linearly completely independent, then a better complexity can be achieved. And if the input and output mass are completely linearly dependent, then the complexity becomes like this. And if they are completely independent, then the complexity becomes like this. And in the independent case, we can sometimes obtain the quadratic speed up. And similarly, we also obtain speed up for zero correlation linear distinction. For completely linearly dependent linear mass, we obtain this complexity. And if linear masks are independent, then we obtain this complexity. And again, for the independent case, we obtain some quadratic speed up for some cases. And since the independent case corresponds to integral distinguishers based on balance functions, we also achieve similar speed up for such distinguisher. And so we achieve the quantum speed up for various distinguishers in the like this. And in our paper, we showed some attacks on complete schemes, but I don't have enough time to explain details today. So please read our paper for details. And instead, I'd like to explain some further applications of our new technique, CEA. So first, I'd like to remark that usual linear cryptanalysis, very roughly speaking, linear cryptanalysis assumes that the basic operations in the cipher are XOR operations. I mean, the key additions and additions in basic ciphers, they are assumed to be XOR operations. But in some ciphers, like NIST standard FPE FF3, such XORs are replaced with another operation like modular additions. And in such a case, we have to use the generalized linear cryptanalysis technique instead. And our technique, quantum technique, CEA, can also be used to such a generalized technique by replacing the Adamar operation in our quantum algorithm with the general quantum Fourier transform. And next, I'd like to explain about some possibility of more than quadratic speedup. So in some integral distinguishers, some integral properties is multiple multidimensional zero correlation linear approximation. And so in some specific cases, we can achieve more than a quadratic speedup by using CEA. For instance, recall that the integral property of the 2.5 round AES looks like this. If the one cell of the input takes all values, then every cell of the output also takes all values. And now we have 16 choices about which cell to activate. And activating the ith input cell corresponds to the situation that the ith byte of input mass alpha is 0 in multidimensional zero correlation linear distinguisher. This means that we have 16 multidimensional zero correlation linear approximations. And if we have such many multidimensional zero correlation linear approximations, sometimes our technique leads to a more than quadratic speedup. And actually, the 2.5 round AES itself is not so much interesting, but if we consider a 4-bit toy cell cipher with the same integral property like this, then the cipher can be distinguished by just a single quantum query by using CEA. And I think such a single query distinguisher is almost impossible in classical test. So I think this is another interesting example of more than quadratic speedup. And next, I'd like to provide some discussions about limitations of our technique and some future works. The first limitation of our technique is that it is unclear how to combine our technique with FFT-based key recovery. So in the classical technique, usually distinguishers extend to key recovery attack. And sometimes they are done by using advanced techniques based on FFT, fast Fourier transform. And recently, Andres Rotenroka showed a quantum version of FFT-based key recovery, but the attack is mainly one-dimensional, and the technique is completely different from ours. So it is unclear whether it can be combined with ours. And so it will be interesting to investigate this topic. And another limitation of our technique is that it is inapplicable to integral distinguishers based on their sum properties. So usually there are some properties lead to breaking more than properties. So it will be also interesting to investigate such topics. And finally, investigating other more than quadratic speedup is also important future because in the previous slide I showed some possibility of more than quadratic speedup, but so far I found such speedup only for 4-bit cell toy cipher. So it will be important to find more than quadratic speedup for more quadratic type. And finally, I'd like to summarize today's topic. So in our paper, we found utmost quadratic quantum speedup for multi-dimensional and multi-dimensional telecombination linear distinguisher. And the speedup is achieved by using a modified version of the subroutine of Simon's algorithm. And the technique can be adapted to generalized linear distinguishers. And if multiple multi-dimensional linear approximations are available, sometimes a more than quadratic speedup is possible in some specific cases. And finally, further research is needed on how to combine our technique with FFT-based key recovery. That's all. Thank you for your attention.
There any question? It's all interesting further. And I have a question that is, as continuous speed is possible for differential distinguisher of differential linear distinguisher.
Yes, actually, for differential distinguishers, we can, I think we can achieve quadratic speedup more easily. So, yeah, for differential distinguishers, we can achieve quadratic speedup easily. And for differential linear distinguishers, actually, I haven't studied it, so it will be also a nice future.
Any other question? Let's thank the speaker.
Thank you.
So the last talk of the session, paper is entitled Exact Security Analysis of ASCON. The authors are Ishwaji Chakraborty, Chandrananda, and Renu Nandi, and Chandrananda will present.
Thank you for the introduction. Good afternoon, everyone. I am Chandran, and in this presentation, I will talk about the exact security analysis of ASCON. This is a joint work with Vishwajit and Mridul. So first, I'll run through the presentation. So first I'll introduce the ASCON AEAD mode. I'm quite sure everyone here knows about ASCON, but still I'll talk about it a bit. And then I'll talk about the existing security analysis on ASCON. Then I'll move into our main result. I'll interpret it in terms of the NIST lightweight competition criteria, and I'll even discuss the tightness of our bounds. And then I'll just give a overview of our proof, and I will conclude the talk after that. So, to introduce the ASCON mode of operation. So, ASCON mode is similar to the duplex modes of operation, but not quite. I mean, like the duplex mode, the ASCON mode is also divided into three steps: the initialization, the data processing, and the finalization. But in the initialization and finalization steps, there are some key XORs which are in addition to the duplex mode. Like in the initialization phase, we have some key additions after the permutation. And then in the data processing step, so this step is exactly the same as the duplex mode. So we take the input, so which is actually the output of the initialization phase, and then for encryption queries we take the associated data and message, and for decryption queries we take the associated data and ciphertext, and we uh, generate a final state which we call F, and then again in the finalization step, so it is different than generic duplex because the key is added both before the permutation and after the permutation, and so it takes the state F and the input the K, and for so the key F, so the state F and the key K, and for encryption queries it generates the tag, and for the decryption queries it checks if the tag is verified. If it's verified, then it outputs the message. And so now, yes. So now moving on to the existing security analysis of ASCON. So the ASCON lacks a dedicated security analysis. So before us, we observed that all existing studies considered it a derivative of the duplex construction, even though we show that it has some key additions. So, but this was not studied in detail in a provable security sort of way. Only it was added to stop leakages. So the based on bounds on duplex are of the order dg by 2 to the c, where d and t are the data and time complexities, and c denotes the capacity of the underlying sponge function. So, I mean, actually, d here is not the full data complexity. You can take d to be the number of decryption queries, but in the worst case setting, the decryption queries can be one block, and then it can be the full data complexity order-wise. So our goal is to do better because ASCON has some extra key additions. So our goal is to get better bounds than this. So before going to the theorem, so I'll discuss the security models that we are operating on. So we analyze the security of ASCON in the random permutation model. So in reality, there is one ASCON permutation. Let us call it P, and then there are different round numbers like P to the A and P to the B. Then for the initialization and finalization phase, it's the actually P to the A is used as a permutation, and for all other things in between, the P to the B is used. Generally, A is greater than B. But to model things in the random permutation model, you can do two things. You can either take the same permutation, or you can take independent permutations. So generally taking the same permutation makes the proof harder, and if you prove it for same permutation, it generally holds for independent permutations. So we take only one random permutation. And so the adversary can perform encryption, decryption, and bidirectional permutation queries in any order. And we also consider only the non-spating adversaries. That is, the adversary can reuse nonces for the decryption queries, but for encryption queries, so two queries cannot have the same nonce. And the final thing we assume is that the key size is at least as large as the tag size. This is required because we want to mask the entire tag. So one other thing regarding the key size is we also need the key size to be smaller than the capacity because the key is added in the capacity part. So if the key is not added gives larger than the capacity, then it might require some extra analysis. So now I move on to the our main theorem. So if kappa and tau denote the key size and tag size respectively, then for any adversary A with data complexity D and time complexity T, the AEAD advantage of the adversary against ASCON is of the order T by 2 to the C plus T by 2 to the kappa plus D by 2 to the tau. So this is much better than this dt by 2 power c, which was already there. So now regarding the interpretation of the result, so the needs requirement was that the data complexity is around 2 power 50 bytes. So the time complexity is around 2 to the 112, and the key size needed to be more than 128 bits, and the tag size needs to be at least 664 bits. So if we put these requirements in our equation, then we can see that t by since t is at most 2 to the power 112, so taking c and taking capacity and the key size greater than 112 bits, slightly larger than 112 bits, and tag size greater than 53 bits works. So what we do is our bound shows that even when we reduce the tag to 64 bits and the capacity to 136 bits, so I am coming why I am taking exactly 136 bits. So our analysis works. So this implies that the ASCON AED can be made almost 50% more efficient without degrading the security. So at this point, so I would like to point some correction in our original paper. So in our original paper, it was mentioned that the capacity can be reduced to 128 bits. So 128 bit comes because the capacity can only be added in the, so the key can only be added in the capacity. So the capacity needs to be greater than equal to the key size. But if you take the capacity to be exactly equal to the key size, then in a special case when there is no associated data and only one block message, then these two keys they cancel each other, and our proof technique does not exactly work. So we have a hunch that it will still work, but not with the exact same proof technique. The proof technique needs to be modified. So we just revise with the 1 byte extra capacity. So from 128 we increase it to 136, and so this has been corrected and can be found in the EPIN archive. So we also show that the bounds we achieve are tight. So attacks of the order t by 2 to the c can be constructed by observing state collisions in permutation queries. So when I say t by 2 to the c, it is almost always d plus t by 2 to the c, because you can also construct state collisions using uh, encryption and decryption queries. But since t is larger than d, we are saying only the order is only t. So, and generic key guessing attacks in permutation queries are of the order t by 2 to the kappa, and generic tag guessing attacks in online queries, mostly decryption queries, are of the order t by 2 to the tau. So, since our bound has these three terms as their orders, so this shows that our results are tight. So now I'll just give a brief overview of our group. So we employ the H coefficient technique for our group to employ the age coefficient technique, you need two worlds, the real world and the ideal world. So I will describe the two worlds one by one. So in the real world, a key k and a random permutation pi are sampled independently, and all the queries are then responded to honestly. And then we have the transcript. So the transcript consists of all inputs and outputs corresponding to encryption, decryption, and primitive queries. But we also give out some more. So we also construct an extended transcript. So in addition to this, the extended transcript also contains all the inputs and outputs of the permutation calls corresponding to the encryption and decryption queries. So for all the encryption and decryption queries, there will be permutation calls. So we also give out the inputs and outputs of that. So now we move on to the ideal world. So the ideal world consists of two phases, the online phase and the offline phase. In the online phase, so all the encryption queries are responded to randomly. That is, if you give any query of the form NAM, that is non-substrate data and message, it gives a ciphertext and a tag randomly. And of course, the ciphertext and the message has to be of the same size. And all the decryption queries are rejected, and all permutation queries are responded to faithfully. So that by faithfully, I mean we keep a list, and if the query is already a part of the list, then we give already the output in the list. Otherwise, we give out a random output and we keep it as a part of the list. And then in the offline phase, we sample all the intermediate variables, and like in the real world, we generate the extended transcript likewise. So now the online phase is very simple, because I mean you either give out random outputs for encryption queries, you fully reject for decryption queries, or you just respond to permutation queries faithfully. So in the offline phase, we need to make sure that this works. So we need to give out the intermediate variables in this way. So I give a bit detail of the offline phase. So the offline phase proceeds in stages. It starts with the permutation query transcript, which we call P, and then first we sample all the intermediate variables for encryption queries. So by intermediate variables, I mean I don't get. So we have not yet sampled any key. So we leave out the initialization phase and the finalization phase. So we only talk about the data processing phase. So we set all the inputs and outputs of the permutation related to the data processing phase, and we give out it as PE, and then we randomly extend our permutation query transcript P to P1 by setting the input outputs for decryption queries. So for that, we use a lazy sampling sort of thing. So we do a random random extension. So if it, and we get P as a union of P1, which we got by random extension, and then the P, and then finally we sample the key K, and we set the input output pairs first for the initialization phase and then for the finalization phase. So correspondingly, we update P2 twice to obtain what we call P-fill. So P-fill along with the inputs and outputs of encryption queries and decryption queries gives us our extended transcript. So in this phase, the offline phase of the ideal world, so we encounter some bad events. So bad events occur in three main ways. So first, bad event occurs when the variables sampled are not permutation compatible. So this is because the random extension function that we use is a function and not exactly a permutation. So whenever we use a random extension, there is a possibility that the variables that we sampled are not permutation compatible. So we show that the order of these events are t by 2 to the c and t by 2 to the kappa. And we also have a bad event when there is a correct forging, but the order of this event is not significant in our analysis. and yes, and we also have a bad event when decryption queries are not rejected, because we already said that the outputs of our decryption queries as reject, so we need them to be rejected. So if this is not rejected, then we have a bad event, and the order of this bad event is d by 2 to the tau. So these three terms are the terms of our bound, and so after this, so we get some bad transcripts and some good transcripts, and then we use the coefficient H technique to get our proof. And so now I conclude, and there are also some possible extensions of our paper which we are working on and stuff. So the key enabler of the proof is the double keyed finalization of S1. So as I've already mentioned, it has both a double keyed initialization and a finalization. So for this analysis, we did not take advantage of the double keyed initialization much. Only the double key finalization played a huge role in our proof, and this is for this design tweak that we have our result. And another thing is that the analysis does not directly apply to other key response based construction, even with weaker security. So the best known bound for generic duplex type constructions is still dt by 2 to the 6, and there is still no attack of this order. So this bound is not tight, and this is an ongoing work. Like how can we in either increase the security for show increased security for duplex based constructions, or give an attack showing that it cannot be improved. And then finally, in the multi-user setting, so we think the bound degrades to mu t by 2 to the kappa, where mu denotes the number of users. But this is a hunch. Exactly our analysis does not work. So a separate analysis is required. But what we can see is if the bound, so we know that the mu t by 2 to the kappa term cannot be, you cannot get rid of this term from, so the other terms we are not sure, but this term will be here. But so if this term is here, then in the lightweight setting, so if the key size is 128 bits and the t is to the 112, then if the number of users is more than, I mean, a small power of 2, say 2 to the 15 will give half. So if there are too many users, then the S1 is not secure in this random permutation model. And also interesting would be having a tight bound for the authenticity security of S1 in the non-misuse setting. And we are currently working on them. So if someone has any ideas, you can communicate with us. And so thank you. If there are any questions or comments.
We have of course time for questions. I do have one question. So basically, your new proof indicates that potentially the thing has gone a bit faster. This is in the setting, for example, where it's not respecting.
Yes.
In case you were advised the designers to actually make this change, did you analyze what would be the impact on other settings like non-string resistance, etc.? Like if you actually change the
yes, so we are working on it. So we think, but as so I think it works, but I mean, but we are working in the random permutation model, so we are not sure. So if you change certain stuff, if there will be something related to the S1 permutation. But one thing is, so since we are increasing the rate here, so I think the rate can be increased to 192 bits and the capacity can be decreased to 128 bits. So if you recall, there are two variants of ASCON, 128 and 128A. So when they update the rate from 64 bits to 128 bits, they also increase the permutation rounds from 6 to 8. So if you increase the rate even more, so it might be you need more rounds for B, but otherwise I think it might work.
On the proof level, you mean on the
Yeah.
board level?
Yes, it's not.
Other question? Let's thank the speaker and all the speakers for the session again. I think we have a long break.